Why does a rubber band stretch so easily while a steel beam hardly bends at all? Engineers and physicists use several material properties to answer questions like these. In this lesson, we'll explore stress, strain, Young's modulus, strength, stiffness, and toughness. Together, these concepts help us understand how materials respond to forces and why some materials perform better than others in engineering applications. When a force is applied to a material, the material changes shape. This change is called deformation. Small forces usually produce small deformations, while larger forces produce larger changes. If the force is removed and the material returns to its original shape, the deformation is temporary. Understanding how materials deform is the first step toward understanding their material mechanical properties. Stress describes how concentrated a force is within a material. It is defined as force divided by area. For example, if a force is 100 pounds is applied to an area of 1 square inch, the resulting stress is 100 pounds per square inch, or 100 psi. Engineers use stress because it allows materials of different sizes to be compared on an equal basis. Strain measures how much a material changes length relative to its original length. It is defined as the change in length divided by the original length. Because strain is a ratio of two lengths, it has no units. In most engineering situations, strain values are very small, often resulting only tiny changes in shape or size. Young's modulus is one of the most important material properties in engineering. It is defined as stress divided by strain and serves as a measure of stiffness. Materials with large Young's modulus require more stress to produce the same amount of strain. Young's modulus tells us how resistant material is to deformation, but it does not tell us how strong the material is. Different materials have very different values of Young's modulus. Rubber has a very low value and stretches easily. Cardboard has a low value, while wood is moderately stiff. Aluminum is much stiffer and steel is stiffer still. The larger the Young's modulus, the more a material resists deformation under an applied force. These differences help engineers choose the right material for a particular application. Stiffness and strength are related concepts, but they are not the same thing. Stiffness describes how material's resistance to bending or deformation. Strength describes material's resistance to failure. A material may be very stiff but break suddenly, or even may be relatively flexible yet withstand large loads. Good engineering design often requires both adequate stiffness and adequate strength. When a material is loaded, it first behaves elastically. In the elastic region, the material returns to its original shape when the load is removed. If the load becomes too large, the material reaches its yield point and enters the plastic region. In this region, permanent deformation occurs. Even after the load is removed, the material no longer returns completely to its original shape. Toughness describes a material's ability to absorb energy before it fractures. A material can be strong yet brittle, meaning it breaks suddenly with little warning. Tough materials can absorb more energy through bending or deformation before failing. Engineers often value toughness because tough materials are less likely to experience sudden catastrophic failures in real-world applications. A structure's shape can be just as important as the material from which it is made. Engineers often increase stiffness by placing materials farther from the neutral axis. This is why I-beams, box beams, and hollow tubes are commonly used in bridges, buildings, aircraft, and vehicles. Smart geometry can dramatically improve performance without increasing the amount of material used. In this lesson, we introduced several important material properties. Stress measures the force per unit area, while strain measures relative deformation. Young's modulus describes stiffness. Strength refers to resistance to failure, and toughness describes the ability to absorb energy before fracturing. Finally, we saw that geometry plays a major role in structural performance. Together, these concepts form the foundation of material science and engineering design. Thank you for watching, and please leave a comment. I like hearing from my viewers.